what the work was it was a sort of amazing coming together of random matrices, free probability, and the theory of subfactors. There have been sort of precursors. It looked like, because sort of starting right with the work I did in knots and sort of two-dimensional theories, there seemed to be a lot in common with random matrices, large random matrices, and this sort of planar structure of subfactors, which I'm going to talk about. And this work that we did together somehow resolved this problem, and the connection between the two subjects became clear, and there was some enrichment going between the two subjects. So that's what I'd like to talk about. But it's a tough job because there's a lot of background in both subjects, both in random matrices and in subfactors and in all three subjects, really, free probability as well. So I'm going to try to put it all together, and I appreciate that the audience is not expert in any of these fields, so I'm going to start somewhere else completely and remind you of some elementary facts about group representations. And I want to start nice and easy with the theory. We're going to take a group and it's going to be finite. So the theory of representations, at least over complex numbers, of finite groups was pretty complete by the end of the 19th century. So it was a subject that sort of had been conquered in the abstract sense before the 20th century, by the end of the 19th century. And a picture emerged which was really quite satisfactory for at least the abstract theory of the representations of a finite group. And I want to tell you about that and how it works if the group is not finite. And it's going to be the infinite case that's going to be much more interesting to us. So first of all, this very easy case. So the first fact that is quite easy is that any finite dimensional representation, or any representation of a finite group, might as well be unitary. So representations which means nothing but that to each group element of the group G, you have a unitary matrix U sub G acting on some V, which is an inner product space. So the unitary transformation UG preserves this inner product space. And it's also known that any such representation is a direct sum of irreducible representations. Okay? So the question is, the first question that you ask yourself if you have a group and you want to know explicitly what its irreducible representations are, irreducible is enough, then you look for them somewhere. And where do you look for them? Well, there's a theorem which is going to follow from what I say, but it is basically that every irreducible representation is contained in the so-called left regular representation. And I'm going to use fancy notation for G is finite here, but I'm going to say, even so, I'm going to say little L2 G. It's nothing but fancy notation for the functions from G to C. So this is just. I wouldn't really have to do that, but I'm preparing ground, obviously, for later on. So G acts on this by the following formula: lambda G of F on H equals F of G inverse H. So this is just the left translation of the group acting on itself and then transported to functions. Because on functions you have to stick in this inverse here to make it a representation. So we have lambda G, lambda H equals lambda GH. So this is the left regular representation, and it's a simple fact that any irreducible is contained in they're left regular. Okay, so if you were a computer and you wanted to look for them, then you have a place to start. You can just start looking in the representations. And another way of saying this is that there is a projection. It's a projection P. So projection. I'm going to be talking a lot about projections. So the projection means P squared equals P, and P equals P star. A self-adjoint idempotent, and it takes P. Takes L2 of G onto V. And to say that G leaves the subspace V invariant is simply the same thing as saying that lambda G with P is equal to 0. So that it commutes. Lambda G commutes with P for all G. So the study, therefore, of representations of, let me get some more space if I can bring this board over, is that all right? The study, therefore, of unitary representations of the group G is simply the study of projections on L2 of G which commute with the left regular representation. Okay? The whole theory can be made somewhat more algebraic by taking the group algebra. So the group algebra is nothing but the algebra of formal linear combinations. So these are things sigma CGG, where these are scalars. And these linear combinations are to be added in the obvious way and multiplied just according to the group multiplication of G. And every time you have a representation of G, you have a representation of the group algebra. So if you send this on the left regular representation, this would get sent to sigma CG lambda G. And in fact, this is a faithful representation of the group algebra. So you can think of this group algebra, if you like, as being embedded in the endomorphisms of little L2 of G. It's equivalent to talk about these abstract universal G's here or the left regular representation. So we have the situation which I want to make sort of, I want this situation to stick out so that you keep it in mind throughout the talk. We have little L2 of G, and on the left, we have C of G, acting on the left, okay? Just by linear extension of the left regular representation. All right, so a group course, there's left multiplication, there's right multiplication, so you also have a right action of the group algebra by right. So this is left, and this is right. Just by, you just put in this formula here, instead of having G inverse H, you would have HG. And obviously these two actions commute because associativity, left multiplication, right multiplication commute. And the main result of the theory, this sort of sums up the entire theory of group representations of finite groups, is first of all that the right algebra is equal to the left algebra commutant, so centralizer. These things, if you, let me say it in words, perhaps better. If you wanted to know what the algebra is of all linear transformations of this that commute with this, then it's this one here, and vice versa. Perfect symmetry. A beautiful situation. So that's the first thing. The things that commute with the left algebra is the right algebra, and then second, the group algebra itself decomposes as a direct sum of all of the irreducible representations of the matrices of size the dimension of pi of C. So I said actually these two results together tell you the entire abstract theory, sort of everything you need to know about group representations over the complex numbers of a finite group. So since you know this is the structure of the algebra, you know that your projections, the irreducible projections for this one are in here. You can look at them inside this algebra. Okay? So the study, therefore, of group representations, irreducible group representations, is a study of this algebra here. Okay? So this is all, as I said, this was all perfected before the 20th century started. This was all very well understood, perhaps not exactly in this language, but certainly it was all okay. All right, everyone, any questions at this stage? Everything's good, everything's under control, excellent. So now I want to go and tell you a few words about what happened in the 20th century, okay? By trying to do this, extend this work in different directions. The first direction worked fine, and that is for G compact. So we can now decide to replace G by a compact group. Instead of just a finite group, we could have a compact group. So if G is compact, everything works beautifully. G compact. The only thing we have to do is replace little L2 by capital L2. We know that there's a left invariant measure on the group. We can form the capital L2 space, the group acts on it, and every irreducible representation can be obtained as a subspace of capital L2 of G, and all the irreducible representations are still unitary and finite dimensional. Okay, that's fantastic. That's more than one could hope or pray for, but it's true if G is compact. So for a group like the circle or the unitary matrices, the 2x2 unitary matrices, some such group, there is such a theory. The actual explicit obtaining of these irreducible representations will be more complicated. It certainly contains at the very least the theory of Fourier series, in the case where the group is a circle, and all kinds of special functions if the group is, say, a unitary group or an orthogonal group or so, and so on. So, but in principle, the abstract theory goes just like the theory of finite groups. Right, now what about a locally compact group? And here, so I'm thinking, for instance, of a group like SL2R, the 2x2 matrices over the reals of determinant 1. Well, here it becomes interesting. It is no longer true. We can still look at L2 of G dg. There's still a left regular representation and a right regular representation, but it's no longer true that every representation, irreducible unitary representation, is actually contained in here. In fact, only a tiny part of the representation theory of the group we could expect to see here, and those representations get a special name. They're called the discrete series. So a unitary representation of a locally compact group is a subspace of this one, if and only if it's, that's the definition of what it means to be in the discrete series. And they behave a little bit like the representations of finite and compact groups. That's why they're sort of very discrete. That's why they're sort of called a discrete series. All right, so but now I've come to the starting point of the talk. That was all just the background. What about infinite discrete groups? Okay, infinite discrete groups. And just so that the kind of groups that I'm thinking about are groups like free groups on two generators, N generators, or SL, NZ, okay? A bit like this one, except over the integers and not over the reals, and all kinds of other groups that you may or may not have heard of. There's the group S infinity, for instance, of permutations of finite support of an infinite set, something like that. So, question is, we're interested in irreducible representations of groups, and the lesson from finite and compact groups was you should look in the left regular representation. There certainly is a left regular representation. Now this is L2 of G, but of course it has to be, these have to be square summable. The group still acts in the same way. So we would expect to be able to find lots of interesting irreducible representations of the group as subspaces of this Hilbert space, of L2 of G. And here things go wrong in about as bad a way as possible. There aren't any. You can never ever find any. And I want to explain why, and that's going to lead on to this theory of subfactors. Okay. So it's a disaster. The theory just doesn't work at all. You're not going, if you want to look for irreducible representations, and this is the natural place to look, and there's none, except maybe the not even the trivial representation. You're dead in the water. So why is this? Well, it's unfortunate, but one thing does work out quite well. You can try what you like. What you should be looking at, of course, projections. Remember, we said that subspaces here are projections from L2 of G to V, and the projections P have to commute with the left representation. Well, that holds true. That's just pure abstract nonsense. You can certainly get representations by taking projections from L2 of G space that commute with G, but the trouble is that they're never irreducible. This part of the formalism works fine, and so does the algebra. We have C of G. So that picture that I haven't read over here, I want to keep it. Let me just go over to it, because it essentially does not change. So we're going to do the same thing here, but now G has become infinite. So we still have the left regular representation, the right regular representation. They still commute with each other. The question is, are they one another's commutants? This absolutely devastatingly goes wrong, as we're going to see, but the fact that the right and the left are each other's commutants is almost still true. There's only one thing that goes wrong, and that is that if you look at everything that commutes, say with the left regular representation, then that algebra is closed in any topology you want to put on it. Whereas the group algebra itself has no chance of being closed. You know, the group algebra are things with finite support. In the case where the group is infinite, you look at sums. In order to be able to do anything with them, they have to be a finite support. So there's no way that's going to be closed. But so it turns out that all you have to do is put a closure here. If you take the closure in the topology, this is for Neumann's result. If you take the closure in the topology of pointwise convergence, it's still true that the left regular representation is the commutant of the right regular representation, provided you just amplify the algebra. And I'm going to use the following notation. L of G, this is the von Neumann algebra, is the closure of the left regular representation. So this is C of G, so I've closed it. All right? So now when you close it, of course, things can, get screwed up. But I want to assume, but what I want to convince you of is that this decomposition here of the group algebra as a direct sum of matrix algebras goes wrong in as bad a way as you can possibly imagine. Okay, in fact, there's two ways that it goes wrong, but I want to emphasize most of all the first one. And the first one is that it doesn't decompose like this at all, because let me just assume that the group has a certain property. All of these groups, well, no, let me get there. Let me get there by actually seeing what we'd have, how this decomposition went when the group is finite. And the question is, what is the center of the group algebra? What is the center of the group algebra? So This is sort of the whole deal here. What is the center of the group algebra? I feel like people are not really following me, but no one's asking any questions, so it's a bit hard to... right. So let's do this in the finite group, and then we'll see what goes wrong in the infinite case. So the center of the group algebra, well, these are functions. An element is in the group algebra as a formal linear combination of group elements. And what does it mean? What does it mean for this to be in the center? Well, it means that if you take an H and you conjugate by it, you've got to get the same thing. And this means that CGH G inverse is CH for all G and H. This is another way of saying that C is constant on the conjugacy classes. C is constant on the conjugacy classes. All right? And these such functions are called class functions, and they come up, they're the reason for this decomposition, because the irreducible representations is basically as many of them as there are class functions, and well, conjugacy classes, that's a well-known fact, and this is a reflection of it. The center of the group algebra is functions that are constant on conjugacy classes. All right, now let's suppose that we're dealing with one of these groups here, these ones that I'm thinking of, these sort of self-respecting infinite groups. What's the conjugacy classes of these? Let's think about the free group on two generators. Okay, well, since it's free, if you take any element and you start conjugating by everything, what's going to happen? You're going to get an infinite set. Like, as soon as you conjugate by something that's not a power of the element you started with, it's going to be different. And so you're going to get so these groups, it's easy to check with the other ones as well, these groups have the property that all of the conjugacy classes are infinite. So they're groups that are called ICC, infinite conjugacy classes. Now you see, this is trouble for the group algebra. This is big trouble for the group algebra. If we have a sigma CGG, and C is supposed to be constant on conjugacy classes, and all of the conjugacy classes are infinite, then how many C's are there? Remember, C is finite support. It's only non-zero on finitely many elements of the group, but it's got to be constant on conjugacy classes. All of these groups have infinite conjugacy classes, so you had it. The only possible, except of course the class of the identity, that's obviously finite. So we find that this in the center implies CG equals 0 for G different for the identity. So we've now calculated the center of the group algebra of one of these groups, and it's one-dimensional. It's just multiples of the scalars, scalar multiples of the identity. So this decomposition this nice decomposition that we had for finite groups, which use the center and decompose according to the conjugacy class, it just doesn't happen at all. It's killed. There's no such decomposition. Moreover, in order to actually analyze this and take advantage of the symmetry, we had to take the closure of the algebra, which I called the von Neumann algebra, L of G. In these cases, it could be that when you take these limits, you add something to the center, but you don't. It's a very simple matrix computation to deduce that this also no center. Okay, so if the group is ICC, the result is that if the group is ICC, this von Neumann algebra, this closure of the left regular representation, has no center. Well, it has a center. It has the center as the scalars, except C times the identity. right? And that's the reason, that's the first reason that this decomposition, which works so beautifully for finite groups and for compact groups, goes disastrously wrong for infinite discrete groups. A closed star algebra of operators on a Hilbert space, and this is exactly what we were studying in order to try to get unitary group representations, is a factor. This is the definition of the word factor if, let's call it star algebra M, if the center of M is one-dimensional. Okay, so that's factor. And now from what I've said, we have examples of factors. That's what I've been building up to. L of F2 is a factor. So let me remind you for the last time that L of F2 is the algebra generated by the left regular representation of F2 on little l2 of F2, closed. L of SLNZ, L of S infinity, and any discrete group that you care to choose, you will have its factor, its associated factor. And the fact that it is a factor means precisely that this decomposition goes disastrously wrong, and it only gets worse because what von Neumann showed was that these, well, first of all, these factors are of a special kind, as so-called 2-1 factors. By that I mean these ones here, the L of G, where G is a group with infinite conjugacy classes, admit a trace. And the trace comes in a very simple way. If we had the trace on the group algebra, is simply if you take the trace of sigma CGG, we take C of the identity of the group. If we call the identity of the group E, then we define a function on the group algebra which simply picks out the coefficient of the identity. That has the property that the trace of the identity is equal to 1, and the trace of AB equals the trace of BA. Well, it's actually trivial that this particular trace is continuous in the topology for which we close the algebra, so it extends to LG. So we have a factor for Neumann algebra with trivial center, which has a trace on it, a linear function with these two properties. So this is kind of surprising, actually, because there's another factor around which you're supposed to know about, which is if you take a Hilbert space and you take the algebra of all bounded operators, all of them, that's a factor, because sort of stupidly you can't write down an operator which commutes with all other operators unless you're the identity. So this is also a factor. But if H is infinite dimensional, this does not admit a trace like this. I mean, imagine you have infinite matrices, you want to take the trace. Then if you have a matrix which has a 1 somewhere down the diagonal and zeros everywhere else, then obviously its trace must be independent of where you put that 1. Okay, but how can that add up to the identity has 1s all the way down the diagonal, so it can't add up to 1. So these factors are rather different from that particular factor, and von Neumann's definition was that a factor is of type 2-1 if there exists a trace. So there you have it. I've got you the definition of a 2-1 factor and lots of examples. Every time you have one of these groups, you have one. Okay. So the study of these so-called 2-1 factors has been a 20th century and ongoing 21st century enterprise. It's turned out that the theory is extremely rich, perhaps the opposite of what von Neumann thought it would be, but we're still nowhere near understanding what's going on with these 2-1 factors. There's all kinds of questions. In fact, let me tell you right away what everyone probably agrees is now the main open question in the subject. It's a big embarrassment to everyone. So, but I can say what it is. So this is the big question, open question for Neumann. I have everything all set to tell you what it is. I said L, if you take the free group on 2 generators, and we take the L of F2, so this is the group algebra completed, acting on little L2, and then take the closure. And then you can do the same thing with L of F3. So the question is, are they isomorphic? So that, my friends, is a major open problem. No one has been able to, if you didn't take the closure, it's sort of trivial to show that they're not isomorphic, because whatever. But when you take the closure, it's a very subtle process. We're lucky that this trace is so easily extended. And no one has a way of somehow laying hands on the generators or seeing that one of them has 2 generators and one of them has 3 generators. So this is an open problem. And it's a pain, a big thorn in the side of everyone working in the subject. All right, but the title, of course, of the talk was subfactors. So now it's sort of obvious what a subfactor is. There's no argument. We know what a factor is, so therefore we know what a subfactor is. So if this is a factor, M, and a subfactor is just simply a subalgebra of it, which is a factor in its own right. So it's a big one that has no center, and a small one contained in it that has no center. So this is a subfactor. Right, now let me just go back for a second and complete the story of how bad things are with the left regular representation. It's a theorem of von Neumann. So theorem von Neumann that the set of all traces of projections in a 2-1 factor is the whole unit interval. All right, so that's an easy thing to write down, but it probably doesn't mean anything to anyone. I want to give it some more meaning, because this is an extraordinary thing. So suppose that you took, instead of a 2-1 factor, there's something that we all know about which strongly resembles a 2-1 factor. In fact, it satisfies everything that I've said so far. You might say that it should be a 2-1 factor. And that is, what about the n by n matrices? So wake up now. If you've gone to sleep, now's the moment to come back, right? If you're completely lost, come back. So take this statement here. If you take a 2-1 factor, then the set of all traces of projections is equal to the whole unit interval. Now, let's suppose that instead of a 2-1 factor, you have something that really looks like it, which is that well, let me use K, because N is getting used too much. Let's take the K by K matrices, okay? And that certainly has a trace. Just add up the diagonals. And in order that it have this property, the trace of 1 is 1, we have to normalize it. So this is trace of 1 is 1. Then my question for you is, what is the set of all traces of projections? In this case, So someone needs to tell me before I go on. Well, maybe everyone's a bit asleep, but so I'll tell you. Well, I won't tell you. We'll get there, right? So, what is a projection? What is a projection matrix in finite dimensions? Well, it's a projection onto a subspace. So, if you take the appropriate basis, a projection matrix in finite dimensions just looks like a bunch of ones and then a bunch of zeros. You can always diagonalize it so that it looks like this. What's its trace? Well, it's the number of ones. But we've got to normalize it, so it's the number of ones, let's call that L. Its trace is L over N. So now it's clear what these traces are. It's exactly the set consisting of 0, 1 over N, 1 over K. Sorry, 1 over, that's why he didn't have the answer. 2 over K, 3 over K, up to 1. Okay? So now it's clear what's going on. What this miracle is that these T1 factors have somehow filled in all the gaps between the rational numbers with the same denominator. So this is some kind of, if you think of projections, subspaces, projective geometry, these are some kind of continuous geometries which is coming in. But now we see why things are so bad. If we want to get irreducible representations in the left regular representation, it would have to be a projection in the commutant which commutes with it. So it's a projection that commutes with it. But the left and right representations are essentially the same. So it's got to be a projection in a 2-1 factor. So therefore it has to have a trace, it's like 1 over pi or something like that. But then there's squillions of projections with smaller trace. Between 0 and 1 over pi, you've got a whole big family of projections, which means there's sub-representation, which means that it's not irreducible. There's a smaller projection that's also invariant, then you've got a smaller representation, so it's not irreducible. So there's no way you can ever get irreducible representations in this left regular representation. So it's a totally different flavor of subject from the compact groups or even the locally compact groups. Locally compact, I meant locally compact connected. I mean things like Lie groups and so on. Discrete groups happen to be locally compact, but that's their fault. I mean, they're not really. Huh? Okay. So I need to get. I want to. Does anyone have the time? I don't see any clock in here. So can I borrow maybe borrow someone's watch? So that I have some idea. I don't want to go, if you let me keep on talking, I'll talk until tomorrow morning, so tomorrow morning's not okay. Okay, thanks. Yeah, so I see that I've already done rather badly with the time. I'm way over time, and I've got through about 10% of the talk. So I want to go, now I'll go very quickly through this what is a very nice piece of theory, which is the subfactors, the index of subfactors. So we don't have any subfactors yet, do we? Examples, but you know they're sitting right in front of us. We know a 2-1 factor would be, say, L of G. This is ICC, so think L of F2. So how could you get a subfactor? Just take subgroup, right? So if we take LH, and this is also ICC, then we've got a subfactor. Okay, so for the free group on 2 generators, you could just take any subgroup you like. They're all free, as long as it's not the integers. Then you've got a subfactor. All right, now what I claim is, and this is the thing I'm going to cut short, is that there is a notion of index, MN, for 2-1 factors, or degree of the extension. It's defined in terms of this von Neumann continuous dimension, but what it actually measures is the size of M as a module over N. Okay? So now I'm going to do some intimidation. I'm going to get the answer out of you for what the index is here. So if we take, what I'm saying is there is this notion of index which is defined for all 2-1 factors, and here's two 2-1 factors for H a subgroup of G, and this is supposed to measure the size of the big one measured by the small one. So what's the answer? And it's called index. So what's the answer? It's the index, right? I mean, it couldn't possibly be anything else. Right? You'd have to be completely insane to invent something for that not to be the answer. So that's what it is. So basically, this number, G splits up as cosets, left cosets over H. Well, in the same way, the algebra splits up as a direct sum of a bunch of left L of H modules. And let me do one more intimidation. So just to ram this idea home, so here's another one. Let's suppose that you have a 2-1 factor N, and now I'm going to take the 2-by-2 matrices over N. Then if this is a 2-1 factor, this is also a 2-1 factor. You just take the trace, you add up the traces of the diagonal things. So what is the index here? This is 2-by-2 matrices. So N is contained in the 2-by-2 matrices by diagonal embedding. So this is this. So basically, you're saying how many copies are there of N in the 2-by-2 matrices over N? So what's the answer? So you people have just been too quiet. You've got to say something now. Come on, someone commit themselves. I'm not going on until someone says what the answer is here. Doesn't matter if you're wrong, someone will get it right. How many copies are there of N in the 2-by-2 matrices over N? Sorry? 4. Right? 1, 2, 3, 4. So 2 was a good guess, but 4 is a better guess. Okay, so that's so there we have it. Okay, now so you see what we have with this with these examples is we have this index and we see that we can in this way we can get all integers. Certainly by fiddling with groups, we get all integers as indices of subfactors. On the other hand, I didn't really tell you how, but I said it was defined by this von Neumann theory. The actual definition ends up being the trace of a projection. And you could make this come out as the trace of a projection. And the projection is supposed to have real values. So a priori, this index should be real values, and we've only been able to come up with projections. So the start of this theory was the theorem which solved this problem. And the theorem is, if we have a subfactor and the index is less than or equal to 4, then it is 4 cosine squared pi of n, n equals 3, 4, 5, 6. Okay? That's part 1 of the theorem. Talk about these numbers in a second. So it's A. And B, all these numbers occur, so does any real number. Okay, so this is the so kind of surprising resolution of this problem. We had this index. It was as it was defined, it was some kind of real number, but we could only get integers. And here's the actual answer. So what do these numbers look like? 4 cosine squared pi over n, starting with n equals 3. So I don't know what high school math is like in Brazil, but the first exercise we have to figure out is what's 4 cosine squared pi over 3. Okay, so these are these things with the root 3s and 2s and halves and things. Well, I mean, so some of you should be there already, you know, even some people with slow minds, the older ones among us. The answer is 1. Okay, which is not surprising because certainly the index 1 occurs, right, if you put m equals n. Right, now what about 4 cos squared pi over 4? Square root of 2, blah, blah, blah. 2 is the answer. Okay. Now what about 4 cosine squared pi over 6? Root 3 over 2, root of 3. Okay. But oh, I left one out, didn't I? What about 4 cosine squared pi over 5? Right, now this is one that is known to the, you know, the up-and-coming clever guy in the class at school who fiddles with computers and so on, the nerd. What is this? This has something to do with the golden ratio. It is, in fact, the square of the golden ratio, and it's approximately 2.6180339. Okay, and then these numbers, 4 cos squared pi over 7, so on, and then they converge up to 4, which is the limit, which is 4 cosine squared pi over 0. No, 4 cosine pi over infinity, 4 cosine squared 0. Okay, 4. And then after that, this continuous dimension takes over, and all real numbers occur as the dimensions of these things. So that's the sort of somewhat surprising resolution of this problem. You can imagine if you were trying to prove this thing, and you proved this thing, that as you would, that there's nothing in between 1 and 2, you're trying to decide that whether it's an integer or not. And then you actually say, oh yeah, in fact the 2 is isolated, there's nothing on the other side of 2 either, then it's an integer for sure. But that turned out to not be the case. The ultimate solution was this. All right. Now, I want to essentially reboot the talk. So, we talked about subfactors and I got to this point. Now I'm going to stop, start on a completely different topic, and then eventually come back and hopefully see that there's some connection between these subfactors and this other topic. And the other topic is the theory of random matrices. So this theory, we warmed up with groups, and especially finite groups, which was all over the theory by the beginning of the 20th century. Random matrices didn't get started until much later, until the middle of the 20th century, approximately. And the name that's associated with the start is Wigner, who's perhaps more known as a physicist than a mathematician. And there's a good reason for that, because Wigner wanted to study random matrices for the following reason. You can look at atoms, and atoms, as you know, have a nucleus, and then they have all these electrons spinning around. But as the atomic number gets higher and higher, there's more and more protons and neutrons in the nucleus. And you know, if you've got 50 protons and 50 and 60, 70 neutrons flying around in this very compact space, it's one hell of a complicated system. Okay? And the question is, what are the possible energy levels? In quantum mechanics, you have, you know, all these systems, they have these various energy levels. Well, if you have a super complicated system like that, and you look at the energy levels, then you might suspect that they look pretty much like a random set of energy levels. And in quantum mechanics, the energy levels are given by, there's some self-adjoint operator, which is it's a first approximation, a self-adjoint matrix. And the energy levels is just the spectrum, the set of eigenvalues of A. So Wegener was interested in the question of what does the set of eigenvalues of a random, just take a random large, because it's a large nucleus, just take some random large self-adjoint matrix, what do its eigenvalues look like? Okay? What's the distribution of the eigenvalues of a large matrix? And that's the question that he solved, and I want to tell you, I'm going to have to race a little bit on this, what the answer is. Okay, so the eigenvalue, let's suppose that the eigenvalues are lambda 1 up to lambda, let's suppose that it's a capital, oh shit. We had n's for subfactors, I need another, and we had m, so I need another large number, letter, capital. I'm sorry, I have to use capital N again. So this is n by n. So not the same n as that n over there. Don't get those, nothing to do with it. N is now an integer, right? Like 1,000 or 1,000,000 or Google. Right? A large integer. Not very often that people use Google as a lambda n. The self-adjoint matrix is going to have capital N eigenvalues, and the question is, what is the distribution? Well, you can think of these, if you were just plucking these numbers out of at random from all numbers, and you wanted to know the distribution that you were sampling from, then you would think of them as being random variables, and you would be interested in the moments to figure out the moments. So you're interested in the expected value of lambda 1 to the r plus lambda 2 to the r plus lambda n to the r. If you know this, for r equals 0, 1, 2, and so on, then you essentially know the distribution. You know the moments of the distribution, so you know how they're distributed. But now this is the key, what is the sum of the rth powers of the eigenvalues? What's another way of saying that? Well, I've been softening you up for it, but you didn't know it. But that's the trace, isn't it? It's the trace of a to the r. And I write a capital T because this is the non-normalized trace. The other one, a little t because the identity was equal to 1. But here the trace of the identity would be capital N. Okay? So what we want to figure out, there's a expected value of trace of a to the r. So what we want to figure out, this is what Wegener did, was the expected value of the trace of the rth power of a random self-adjoint matrix. Okay? This is the calculation that I'm about to perform. I'll do it rather rapidly, but you could actually afterwards go back and fill in all the steps. So it's going to rely on a theorem that you'll find in statistics textbook. You'll also find it everywhere in physics textbooks, called Wick's theorem, which says the following. It's about, I'm going to assume, to be precise, I'm going to say that these self-adjoint matrices have Gaussian, the entries are independent Gaussian random variables. And Wick's theorem applies to independent Gaussians, and it says that the expected value, if we have a bunch of independent Gaussians, let's call them x1 up to xk, this is equal to the sum of all of the pairings of the set 1 up to k, of E of xi x pi I. So pairings pi. Okay, so this is a classical theorem, not too hard to prove in probability or statistics or physics, that if you take a product of join the Gaussian random variables, x1 up to xk, then the expectation value of the product is nothing but the sum of the pairings of the indices. So I take I and pair it up with pi of I, and I take the covariance of xi and x pi I. Maybe I have to assume here that the e of xi is equal to 0. I forget this, but to be on the safe side, let's assume that this is true. I think that's correct. Okay, so that's a standard theorem. Find it in all the textbooks. Prove it yourself if you want to. It's quite useful. So now I'm going to attack this problem of calculating the expected value of the trace of a to the r in the most explicit, naive way possible. I'm going to write out the trace of the a to the r explicitly in terms of the matrix elements of A. So this is the expected value of the sum of indices I1 up to IR of A I1, I2, A I2, I3, A I3, I4, and A IN, I1. Okay, all I've done is I've done the matrix multiplication of A by itself R times, and then I've taken the first index equal to the last index and summed them up. So this is explicitly the matrix summation. There's an explicit formula for the trace of A to the R. And now I'm going to make this assumption that these things are mutually random matrices of a certain sort, that the AIJs are mutually Gaussian, are jointly Gaussian, that they're centered equals 0, and that they are as independent as they can possibly be, given that it's a self-adjoint matrix, so that E of AIJ AKL is equal to 0 unless, so this is the constraint of self-adjointness, that the conjugate transpose is equal to the thing. So unless I equals L and J equals K. All right. So now we're going to apply Wick's theorem with this hypothesis, and we're going to apply it to that formula. So we have a product of mutually jointly Gaussian random variables. This is the covariance that we're given, and we just write it out. So now the point is that we can index this sum. We can actually, the way to do this computation is to arrange all of these indices. I'm going to do this very quickly. So let's suppose we're doing R equals 4. And we go I1, I2, I1, I2, I4, I2, I3, and I3, I4. Okay, so here are the indices of these 4, that would be a total of 4 random variables going into the sum. Well, we've got to look at pairing. So let me draw in here what you have to put for a pairing. Here's a possible pairing of these guys. I could pair this one with this one. And then I'm forced to pair this one with this one. This calculation is due to Tuft, by the way, physicist. Well, just to cut a short story even shorter, it turns out that in order, with that particular covariance, almost always you're going to get 0 here, because you'll have an I1 which is different from this pair, will not correspond to this pair. And the only way that it turns out that the only way that you could get a contribution in this sum, in this Wick sum, to the trace of A to the R, is if the index here that you see on I1 is constant along this line here. This has to be I1, and 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 then this has to be I1. Oh dear, things are looking bad. And this has to be I1, this has to be I1. So for this particular pairing, there's only one possible contribution one possible way the indices can be if they're all equal to I1. Okay, so this sum, which a priori was a huge sum, is dramatically reduced to a sum of simply all the indices being equal to 1. Right, now how could you avoid that? Well, you could try a different pairing. And let's try this pairing here. All right, now if the indices have to be constant along the edges of this thing, then this is a free index, and then this is a free index, and then this is a free index. Okay, so the conclusion is you get many, many more, a much bigger contribution to the trace of a to the r, in this case the trace of a to the fourth, from this pairing than you do from this pairing. So the question is, now we're interested in the limit as the size of the matrix tends to infinity. Well, how big was the contribution? Well, every time you had one of these free indices, that contributed a whole factor of capital N. So here you're going to get n cubed, a term looking like n cubed, and here you're going to have a term just looking like n. So in the limit, as n tends to infinity, this term will simply drop out, and you'll be left with this term here. All right? Now what about all the other pairings? Well, the idea is, I've tried to, I've done this a bit quickly, but the idea should be fairly simple, is that the pairings that are really going to contribute as n tends to infinity are the so-called planar pairings. And this was not a planar pairing. You could not embed this thing in the plane, because in order to pair this with this and this with this, they have to cross. And that was the thing. The reason that they had to cross was exactly the thing that limited the size of the contribution to the trace of a to the fourth. Okay? And the result now becomes just a simple, putting in the numbers for this here, that the answer is that the limit as n tends to infinity of the trace, expected value of trace of a to the r, is equal to the number of planar pairings of r points. Okay, so we take r points, 1, 2, 3, 4, 5, 6, r, and we count the number of ways we can pair these points up in the planar way. So there's that way, that's a pairing, and here's another one. And so on. So does anyone happen to know what the answer is to that? The number of ways of pairing up r points. Planar way. I believe there's some combinatorists in the audience. They should surely know. Maybe they're just bashful. So if r happens to be 2p, then the answer is 1 over p plus 1, 2p choose p. Okay? So that's the answer. So that actually solves Wigner's problem. This gives you the distribution, the asymptotic distribution of the eigenvalues of a large random matrix. And when you do the Newton's binomial expansion, you find that the probability density function is this suitably normalized square root of 4 minus x squared. So there's the amazing result of this calculation. If you look at the eigenvalues, distribution of the eigenvalues of a large self-adjoint matrix, it's as if you were sampling numbers from a distribution with this probability density. So in particular, out here you get 0. So it's not Gaussian, it's not like Gaussian things at all. You cannot have, with probability 0, you get large eigenvalues in the suitably normalized eigenvalues in the large n limit. Right, well, I can see my audience is disappearing, so I have to wrap it up quickly, and I'm still only about Well, certainly not halfway through. So that's unrealistic. All right, so what am I going to do? How am I going to finish this off? The next step is to replace, and this is the name relevant for the next step is Voiculescu. The next step is to replace a single random matrix by a bunch of random matrices. So let's suppose that bunch is exactly 2 random matrices. So we have matrices A and B. And I'm assuming that these are independent matrices such that their entries are mutually Gaussian in the same way. But of course now, all of the entries of A are independent of all of the entries of B. Okay? Each A is self-adjoint, A and B are self-adjoint. So their entries are constrained by the fact that they're self-adjoint. So Aij is equal to Aj star, same with B. But all the entries here are equal to all of the, independent of all the entries here. So we take a word like, say, A, B, B, A, B, B, and we want the expected value of the trace of that word. Okay, we can do this game, again, this Tuft game, but instead of putting a single matrix A on the circle, we'll have A, where we have B, B, then there's A, B, B. We do the same argument here. We find that all of these indices, the only thing that contributes in the large N limit are the things, the planar configurations. So we find out that the limit as n tends to infinity of this expected value is nothing but the number of pairings. You see, I could get this from intimidation now. It's the number of planar pairings, just as it was before. So we can imagine pairing this up to this up, and so on. But because of the independence of the A entries from the B entries, the only pairings that can contribute are ones that pair an A to an A and a B to a B. Okay, so this pairing would count. Okay, so now all of a sudden that nice combinatorial formula which gave you that binomial coefficient there doesn't work. It's going to depend on the word. For instance, in this word, in this particular word, how many pairings are you going to get? Well, not so many. For instance, you can't pair these B's with these B's because the A's would have to cross. So there's the answer, and this was Voiculescu, that this trace of, this limit of this trace is actually equal to the number of planar pairings pairing A's to B's and pairing A's to B's, A's to A's and B's to B's. Right, now I really have to finish, so let's have one punchline at least. What do you do with this result? What do you do with this result? For a single matrix, it was clear that what we were doing was we were figuring out what the distribution was of the eigenvalues of this large matrix. What's the meaning of this result? Well, you know, if you take a product of self-adjoint matrices, it's not going to be self-adjoint because they don't commute. So it's not clear what to do with it. But what Voiculescu said was we should take this as defining a rather interesting trace on the algebra, the algebra of polynomials in 2 variables. Okay, so this is something like C of A and B. Okay, that's what this, you know, this limit, or this complicated combinatorial formula on these words, that gives you a linear function from this algebra of non-commutative polynomials. Here's a non-commutative polynomial. Its trace is this number of pairings. So only a few more sentences to go. Once you have a trace like this, you can form a Hilbert space by defining an inner product x, y equals trace of y star x. The algebra of non-commutative polynomials acts on this Hilbert space, and you can take its closure. Okay, so you take this. So this is supposed to take us back to the first part of the lecture where we had the group algebra of a discrete group. We had it acting on a Hilbert space, we took the closure. We do exactly the same here. And Voiculescu's first part of Voiculescu's theorem is that this for Neumann algebra is nothing other than the one that we've already seen, L of F2. Okay? This is the subject of so-called free probability. Right, and this obviously works for Fn, if we had n different variables here. The connection with subfactors is that if you have a subfactor, then you can sort of reverse the arrow and you can construct a matrix, a model, a sort of what's called a matrix model for physicists, in which this behaves, a matrix model, with D random variables, where D is a real number. So the sort of contribution that Guillenay, Schleck-Tenko, and myself made was using the theory of subfactors. We were able to invent matrix models for which all of these combinatorics still work, but they behave as if the number of random matrices, which in the Voiculescu case was 3 or 4 or so on, is actually a real number. Okay, so this is where the for Neumann continuity and the subfactor continuous dimension all comes in. So I'm sorry I've abused time rather badly here. I'm not quite sure how I must have started late or something, because I've never done quite this badly on time. But I'm sorry. Anyway, it's a quite fascinating situation where we now have these matrix models where we have a continuously varying number of matrices. Instead of 2, we might have pi random matrices. Okay, thanks very much. So the question is, what is the connection? We have these 2 matrices, and what's the connection with quantum mechanics? Well, yeah, that's another lecture at least to get me started on that. But so the idea is that if you write down explicitly, instead of just saying that these matrices are jointly Gaussian, you can give a model for them in which the probability space for the matrices is the matrices themselves, and the integral that you're doing when you calculate the expected value is the integral of e to the minus the trace of a squared times dA. And this would be, to get the this is the, basically the probability density is e to the minus trace of a squared dA. So this is the Gaussian, these things are jointly Gaussian, so you'd be, to get another way of saying what this calculation that we did is you're integrating over all capital N by capital N matrices. You're integrating e to the minus trace of a squared times the trace of a to the r. It's just another way of saying it. Well, a physicist looks at that and says quantum mechanics, Gaussians, etc. Which the next thing to do is to put a coupling constant times a potential here. Just some invariant function of the trace. And so the idea is that the things that we were calculating before were the so-called free theory, and then but the really more interesting physical theory, which would be the free Hamiltonian plus a potential. Okay, and physicists have worked a lot on that. There's some beautiful work where they've figured out very complicated, very interesting combinatorial formulas for these, which always involve planar pictures, because you do it by doing Feynman diagrams, and you find out that only the planar Feynman diagrams contribute in the limit, and that's the story. And my 2 co-authors, Guillenay and Schleck-Tenko, have shown that at least you can do this for several random matrices, and at least for very small values of beta, the 2-1 factor that you get is still the free group 2-1 factor. I'm not sure that really answers your question, but it's... Oh, no, sorry. Yeah. No, you have to have sigma. To get more than one matrix, you put them in. So this is a trace of some word. Now, in contrast, if you have more than one random matrix, this problem with a potential becomes extremely difficult to solve, and there's only very few examples where that has been done in any kind of explicit way. We managed to do such an example with a very specific kind of potential coming from the subfactor point of view. Yeah. That's good. So, yeah. So this is a very sharp, very pointed question. It's saying that yeah, that there is some theory, right? So the thing is that the question is, does this look like we're talking about some L of FD, where D is now a real number? So we're talking about, is there some theory of the group with a real number of generators? The answer is absolutely correct. But this notion of L of FD already existed in the von Neumann algebra theory, starting from the work of Voiculescu. Because Voiculescu was trying to solve that problem that I said in the right at the beginning of the talk, this embarrassing problem of whether L of F2 is isomorphic to L of F3. And Voiculescu and his disciples, Dykema and Radulescu, managed to define what they call interpolated free group factors. And so they have an L of FD. And the question becomes, is L of FD isomorphic to some L of F other D? And the question is open, but it's known that if that's true, then they're all isomorphic. And if it's not true for any pair, then they're all non-isomorphic. So this theory that we did had exactly what you said. It had this notion of a free group on D generators to plug into already. That was already there. And your observation is absolutely correct.